Hi, in the last video we have derived boundary layer equation which is presented here from the full Navier-Stokes equations. Okay. So in this video we are going to discuss about Blasius solution to boundary layer equation. Blasius, one of the students of Prandtl who derived boundary layer equation. Prandtl has derived boundary layer equation. Blasius was a student of Prandtl, has provided additional insights into laminar boundary layer flow over a flat plate. Okay, so Blasius considered laminar boundary layer flow over a flat plate. Okay, so for a flat plate, if we consider flow over a flat plate, okay, we are going to develop this boundary layer is going to develop. This is the boundary layer edge. If we consider flow outside the boundary layer, okay, so let's say this is x and this is y, so the u will remain constant along a particular x. Okay, so which means that du by dx is 0 for a flat plate. From Bernoulli's equation you can verify that the pressure gradient is also 0. Okay, so for a flat plate this term goes to 0. Okay, for a flat plate, so the boundary layer equations are further simplified. Okay, but the point to see here is that even after this simplifications, exact solutions are not possible. Okay, so Blasius has used a clever change of what he has used is the very clever change of variable technique, okay, to derive to reduce the system of partial differential equation given here as the boundary layer equation into an ordinary differential equation. Okay, so he has converted the two equation, which is a partial differential equation that are shown here, into a single ordinary differential equation. Okay, so details of this derivation is beyond the scope of the present course, so we will only outline the fundamental idea of Blasius in this lecture. Okay, so before we move on to talk about the exact details of what Blasius has done, we need to discuss a very important concept called self-similarity. Okay, by self-similarity what we mean is that if an unknown is a function of two independent variables, okay, so for example here we are talking about for example we can consider velocity within a boundary layer which is a function of x and y. Okay, if this is if an unknown like velocity is a function of two independent variables, by properly choosing or by properly, I would say, expressing them in a non-dimensional form, okay, then we can eliminate explicit spatial dependency of one variable. Okay, then we can eliminate explicit spatial dependency of one variable. Okay, might be confusing now. Let me present an example. Let us again the example of flow over a flat plate. Okay, and this is x, y, Okay, this is the boundary layer edge. If I draw the velocity profile here, okay, so it looks like that, and then at a different location it looks like here, okay, and at another location it's like this. Okay, so let us say this is x is equal to x1, this is x2, and this is x3. Okay, so you can see from here is that the velocity u is a function of both x. Okay, you can see that when I move along x, the velocity is going to change, and when I move along y, again it is going to change in magnitude. So it's a function of both x and y. This is in the dimensional form. Okay, by self similarity, okay, what we mean is that if we express this in a proper non-dimensional form, okay, so instead of y, I'm going to write y by delta of x, where delta is the thickness of the boundary layer. Okay, delta is the thickness of the boundary layer. As you know, this is a function of x, because as we move along x, the boundary layer thickness is increasing. If we plot this versus u by u infinity, okay, which is the free stream velocity here, okay, all these profiles will fall into a single curve. Okay, it doesn't matter whether you are plotting the velocity profile at x is equal to x1 or x2 or x3, we will get a single velocity profile. Okay, all these curves x1, x2, x3, or you take velocity profile at any location, it all collapse into a single curve. Okay, so in a non-dimensional form, so u is function of x and y, so here u by u infinity is a function of eta, okay, where eta is called self similarity variable, okay, which is equal to y by delta of x. Okay, you can see that here there are two independent variables. Here there is only one, which is a self similarity variable. Okay, so self similarity does not occur for all fluid flows. Okay, only for some very specific set of fluid flow problems for which we can use this self similarity concept. Okay, it is not a very general one, but it is applicable for laminar flow over a boundary layer. Okay, now without going too much into the detail, so what Blasius has done is that Blasius introduced stream function. Okay, I hope you know what a stream function is. Existence of stream function guarantees automatic satisfaction of mass conservation. Okay, so which is some function of eta, which is unknown. Okay, now we are talking about stream function, so we don't have to consider mass conservation equation. So he has substituted this unknown function into the x momentum equation. Okay, he substituted psi in the x momentum equation. Okay, yeah, psi in x momentum to get the following equation, which is a 2 f dash, sorry, triple dash plus f double dash is 0. Okay, we started off with the system of partial differential equation. We reduced it to a third order. Okay, we reduced it to a third order ordinary ordinary differential equation. Okay, and this is the Blasius equation. Okay, so But even after such simplification, we started with Navier-Stokes. We started with Navier-Stokes. Okay, we got boundary layer equations. Okay, then we consider flat plate flow. A boundary layer flow or a flat plate, and we have got Blasius equation, which is a simple third order ODE. Okay, even after such simplifications, Blasius solution is not possible to solve it analytically. Okay, so even this third order ordinary differential equation, which looks simple, cannot be solved analytically. By the way, here when we say f dash, we are talking about the derivative. Okay, f dash is first derivative, f double dash is second derivative, and f triple dash is third derivative of f with respect to eta. Okay, so f dash is df by d eta, as shown mentioned there. Okay, so what Blasius has done is he has used a numerical methods to get the solution for this equation. Okay, so Blasius, in the next semester you have a course on numerical analysis, where you will learn more about how to solve ordinary differential equations using numerical methods. So I will not get into the details of this. So Blasius used numerical methods to solve this equation. Okay, and then he has obtained the following velocity profile. Okay, if you plot the non-dimensional form with respect to eta, okay, you are going to get the velocity profile. Okay, it is such that the u by u infinity is 0.99 at eta is 5. Okay, and he has also obtained a boundary layer thickness, okay, which is delta by x is 5 by square root of rex, where when Reynolds number with respect to x, we mean ux by nu. The length scale is used. Here is the distance from the leading edge of the plate. Okay, then displacement thickness, which is delta star by x is 1 point. Okay, and momentum thickness, theta by x okay, and in addition to this, he has obtained an expression for wall shear stress. Tau w is 0.332 square root of rho mu by x. Okay, mu is the dynamic viscosity, right? So if we plot wall shear stress with respect to distance from the leading edge of the plate, we see that it is a decreasing function. Okay, wall shear is proportional to 1 over square root of x. So as x increases, the wall shear decreases. Can you guess why is it so? No. So if we consider the flat plate, and then we consider the a particle that is adjacent to the ball. Okay, so we have discussed that the particle that is attached to the wall due to no slip tries to pull this back, or try to reduce the velocity of the adjacent fluid particle. Okay, so let us say this particle starts here with velocity u is 1. When it goes here, due to the action of this one, the velocity is, let us say, reduced to 0.8. Okay, then it moves further here, and again there are some fluid particles sticking to the wall, it again tries to pull this, reduces this to 0.65. So as it goes along here, the velocity of the particle reduces. Okay, so as a result, the gradient du by dy at the wall reduces. Okay, because the adjacent layers are continuously slowed down by the viscous action. Okay, so when you know that shear stress is proportional to the velocity gradient, when this reduces as x, reduces with x, tau also will reduce. Okay, which is what we are seeing here. Okay, thank you.